but I would also encourage you guys to always be attentive if I'm not recording. Just remind me, because I'm trying to be good, but I'm not perfect, as you've probably noticed if you've watched the videos. So it's recorded. That's exciting. Anything else?
Are we going to be like doing stuff like how the homework is, those kind of questions?
Yep. So the exam is broken up into two parts. One part is the closed book section. That is probably more like a traditional exam. They're all, what was the right word for it? They're all open-ended questions, but for that section, they typically have just one correct answer. We'll take it here together on that day. If you want to put your screen on mute, that is fine. But if there's any questions that come up, then we can address those questions. And since the exam is honor exam, and we're just going to follow an honor code, my basis is for the closed book section, you don't look at anything. For the open book section, that's going to be more like the homeworks, in that you'll just have different data sets, different questions, different issues. For the first one, there tends to be really only a few ways you can address the questions. In the later exams, later in the semesters, there's tend to be more diversity in what you can actually do with the prompts. But in the open book, they're real data. You know, you're playing with real information. The data may not be perfect. In fact, it won't be. That's boring. You know, let's give you some real stuff, and you got to sort of figure it out. But they're not designed to be real yet. They're just a few little things you got to pay attention to. Questions with that?
No, but can you put the p-value PowerPoint and this PowerPoint on Canvas, please?
Yes, I can. And while we're answering questions, I'll just do that in the background.
Thank you.
So one question that does come up is how to study for it. The first thing you want to do is sort of the basic minimum. You need to know the material. You need to know what different things are. You know, you need to know what a p-value says, what it does not. You need to know what hypotheses are, what they mean, what they're not. You need to know the different statistical philosophies. We use one of them in this class, but you need to know both of them. You need to know sort of the statistical concepts that we've talked about. You need to know those. Then the second half is you really need to apply. So you can even goof around with the data sets that I've given you in class, as well as the data sets you've had in homework, and try different things with them. A lot of people came to office hours today, so I will try to remember to post the link the day before each week. And Dom, if you can help me remember that, that would be good, so that you can participate. But a lot of people who came to office hours today were sort of starting with the base questions and then trying to do different things with it. And that's really what the class is. Little small word of caution. We're not really about interpreting reasons why things are happening. That's not this class. This class is about the analyses describing patterns, the explanation for those patterns. That's when you take a class like this and you bring it into ecology or cell biology, you know, where you have a much firmer sense of the biology behind the process. But with that said, we're still biologists first. Questions? Which will give me time to actually post the notes.
You were
I did
saying,
publish the.
oh, go ahead.
I just published the p-value PowerPoint.
Did you publish the one that I changed?
Take a look
at that.
Yeah, we'll worry about it later.
Yep. Awesome. Thank you.
Yeah. I was going to ask on the closed book part of the exam, you said they're all open-ended questions, like short answer, no
Yeah.
multiple choice.
Yeah, I mean, there's some multiple choice, kind of. Yeah, sure. I could see. Yeah. There's at least one or two.
Okay.
There's not that many questions, and the questions are meant to be addressed and answered within the short time frame of the class.
Okay.
How much time are we gonna have for the sections?
The answer is you have as much time as you want until it's due. With the closed book, I mean, if you want more than an hour and 45 minutes, fine. But I'll be discouraging that because at that point, all you're doing is playing head games with yourself. The average person, the closed book will take them between, I would say, 15 minutes to an hour. And that normally depends on sort of the depth of the answer and how quickly you sort of think through things. The open book, totally open to how long you want to take. And people can take a long time. Eventually you're just playing head games with yourself. But yeah. So Tristan asks, is there any source material study guides that should practice? Yeah, the homework, the data sets we use in class, and use the notes, use the videos, all of that. And one of the things, and don't hesitate to take screen captures anytime we're sharing something. The questions I ask in class really kind of give you a sense for how I think about information and the type of questions that I like to ask in general. You know, I don't change my personality in class versus when I'm writing a test. I tend to get really excited about tests. And if I'm excited about tests, it means that you get to think during the test. And the best tests I write are when you're actually learning during the process. That rocks my world. Doesn't happen every time, but that's what I'm always aspiring to do.
So during the closed, like, short answer section, we aren't to use any resources or whatever. But during the other part where we're actually doing like the stuff in our studio, are we allowed to use anything, or is that also the same thing?
In fact, I'll tell you what you're not allowed to use.
Okay.
You are not allowed to use each other. You are not allowed to use Dom or myself. And you're not allowed to use anyone else with expertise in person regarding our studio or data analysis.
Okay, but like our previous notes and everything are
You
free
are
game.
welcome to use your previous notes. You're welcome to use the videos. You are welcome to use Google. You are welcome to use different forms and RSSs and anything that you can find. So the idea behind the open book is being professional with data. And when you're professional with data and you have an issue, you go seek out help with it. And all of that is fair game.
Thank you.
Cool? Any
Okay.
other questions with the test?
For the open book section, will we have to turn it in that same day before midnight, or when will it be due?
I like to make things due Saturday morning at around 5 a.m. And the reason I like to make things due Saturday morning at 5 a.m. is because my family are a bunch of slovenly fools that like to sleep in till like 8 or 9 o'clock. And I like to wake up at 5:15. As a result, I'm able to wake up, get in front of my computer, and start grading when no one else in the house is awake. So I will probably give you until Saturday morning at 5 a.m.
Wait, sorry, I missed that. Saturday morning till 5 a.m. for what?
to turn in the open book. That would probably be the call.
Are we going to start that during class time, or is class time just for the closed book?
So for class time, you're going to do the closed book. Once you are done with the closed book, I'm going to encourage you to take a look at the open book. If you have specific questions, then we can address those there. I might go into a breakout or send you and Dom into a breakout so you can address those questions. And then when you feel set, you can go on.
Okay.
And for the open book, I would encourage you to think, give it a little bit of digestion time, and then come back at it. But you'll pick your strategy you want for that. Anything else? Last little comment in terms of when things are due. You're a professional, which means that if Saturday morning works for me, but for some reason, as a class, you guys can't get at it until Friday evening and you need it done on Sunday morning, you just tell me. And we make that accommodation, we make that adjustment. Because that's what the professional world is. There are a few things with our strict deadlines. The final exam will have a strict deadline because I have to submit it, the grades back to the university. But other things are negotiable based on what you all need. Make sense? What I need is a negotiation before we start. Any last questions with the exam? All right.
Is there any way to take it earlier?
No, because I got to write it. And there are two things with that. I'm not going to have the time to write it until at least next Monday. So the day before. I have a basic structure of one I want, but then I always have things I want to play around with.
Okay.
Sorry. Anything else? Okay. So the two sets of notes are there. I might update them after class if there's some information that I added, which are not here, but just remind me at the end of the class. And then we will find a point today where we want to stop. This is the last of our conceptual topics. And this is maybe the most statistics according to Gunnels talk that you'll get through the semester. These are my thoughts about these three topics, which annoy me to no end. So before we start getting into all the tests and the procedures, let's deal with the last of these concepts. The three evils of statistics. We already know the three evil words in science. It, that, and they. Terrible words. Strike them from your vocabulary. These are the three evil concepts of stats: normality, outliers, and transformations. Cool? So, one of the things to remember is in life, there are many different types of distributions, and different distributions have different structures. And what you're looking at in each one of these cases essentially is a density plot, much like you guys were creating last week in R, or last class in R. And many times distributions are uniform, which means that you have equal numbers, equal proportions of each group within a range. Sometimes you can have distributions which are bimodal, where you'll have multiple peaks and multiple troughs. So we have a lot of small values. We have a lot of large values, but very few intermediate values. Can anyone think of something in nature which shows very clear bimodal, trimodal, quadrimodal distributions? Okay, so I want to think of something in nature that shows very clear uniform distribution.
The clouds. The clouds are pretty uniform. The cloud cover over there.
I actually think that's a really good observation. So the lower level of clouds at any one point in time tend to be relatively uniform, because the actual creation of the cloud, that saturation point for the water, is very dependent on the amount of water and the air temperature and the air pressure, which happens at a uniform scale. So not the top of the cloud, but the bottom of the cloud relative to the plane of the planet. Yeah, very uniform at any one point in time. The one that was popping in my head that always kind of makes me geek out is forest canopies in hurricane-prone environments. They tend to be very uniform heights, because any tree that gets above it, what happens to that tree during a hurricane?
It dies.
It dies. It gets topped. It gets clobbered out. So you can always kind of look at a forest and see whether they have regular hurricanes based on whether the canopy tends to be fairly uniform in height. What about bimodal, trimodal, quadrimodal? What are some nature things that show that distribution? Someone not named Tristan this time. Or I could go random. Great, Heather B, you are actually the first up.
My goodness. I have no idea.
Oh, come on now. Nature. I will tell you all, it makes me very happy. Like these are one of my loves. I have a lot of loves, but this is definitely one of my loves.
What about, I don't know.
A lot of ant species. The workers show multimodal distributions where you'll have small workers and you'll have large workers. Leafcutter ants have at least 5 modes within the size distribution of those animals, from very, very tiny ants that fight off parasitoid flies to huge ants with massive mandibles that fight off predatory animals like, ant lions and aardvarks, stuff like that. So a lot of ants show caste systems, and those castes are multimodal distributions. A lot of things also show Poisson distribution, which looks like, slightly skewed. In fact, a lot of natural distributions of plants within an environment show Poisson, where you'll have a lot of individuals that are fairly close proximity to each other, and then you have a few that are very spread out. Each of these are common distributions in nature. When we look at distributions, we can describe the overall quality of them. And one aspect of their description is their skewness. And when we talk about skew, what we're talking about is you can have a unimodal hump, but one side of the range stretches out disproportionately far. If it is left skew or negative skew, then it means the small range. You have a few very small sized or very small measured examples. Contrast to that is a positive skew, where you can have some very large and just a few very extreme large values in that measurement. Can someone think of an example for either one of these two? And for that, Alex, you're up, buddy.
Possibly if you were to say like the size of like a giraffe, you're not gonna have too many like extremely small values on like their height.
Actually, I think a giraffe is a great example relative to other mammals.
Yeah.
Most mammals are small. Shrews, rodents, beavers. A few animals are intermediate size, not as common, things like dogs, but a few, very, very small number of species are absolutely enormous. Giraffe is a great example of that. So the distribution of mammals relative to size, great example of that. The one that always pops into my head is income distribution of people. Most people tend to be in some sort of median location, but then you have a few individuals that are excessively wealthy relative to the vast majority of individuals. Both of those, Alex, very clever observation, are positive skew. Can someone think of a negative skew example?
Would age at death be an example of negative skew? Because most people die when they're older, so like over 50, but then you have a couple instances of people dying very young.
I had no answer, Casey, so I'm actually really impressed. I think that's pretty good, especially in modern developed societies. So lifespan of humans was not always this structure. But as we've had more medicine and as we've had more childcare, the idea of early death has become lower and lower and lower. It's still present, but we tend to survive into early adulthood. And then we have sort of a mode median of that period. I'm getting closer and closer every day, and then it starts to drop off at that point.
So would a negative skew in death rate or death age represent like a society that can preserve its population or has better longevity?
Better longevity and better early natal care are most likely some of the explanations behind that. Yeah. Human death rates used to actually look multimodal, where human death rates were very high at birth. And then you would have quite a bit of survival, and then they would start to grow again as individuals got older. So, yeah.
Probably a peak in there to around mid-age.
Well, mid-age would be the limit, I mean, at earlier days, I'm done. I had sung my song. It was a good song to sing, but I would be out and you would have a much younger professor teaching the class. Of course, probably not through Zoom. Questions with that? Great examples. Love it. Okay, So then we have something called kurtosis. Now, kurtosis is awesome for two reasons. One, you get to say kurtosis. Say it.
Kurtosis.
Kurtosis.
It feels good, doesn't it? It is a good word to say. And kurtosis describes sort of a property of the variation around a central tendency. And if you have negative kurtosis, what you have is you have a central tendency. I think my computer was talking to me. You have a central tendency, but there's a tremendous amount of variation around that central tendency. So it spreads out, almost looking a little uniform, if you remember that from earlier. But eventually you see drop off at both extremes. And if you have positive kurtosis, what it means is that you have very little variation around the central tendency. And most of the distribution tends to be right in that middle. Any examples of those you can think of?
Could that be like how barnacles are on like a post, for example? You have like concentrations of different species, and then as it shifts in depth, the species change. So you have concentration in the middle, and then on the outskirts of each species, you have like less and less.
So almost sort of a positive
Like
kurtosis for the individual
yeah.
species in that little niche that they show up on
Yeah.
that. I think that might be fair. I mean, we'd have to measure that one, but I got the logic that you're describing there.
Okay.
Can someone think of an example for negative kurtosis?
Maybe the times that people are awake. Like for the most part, the human population is awake at the same time, give or take a few hours. Like say from 8 a.m. to 10 p.m., the majority of humans are awake, but then there's those few outliers that like stay up later, don't go to bed.
I think that actually could be very true. Or the amount of time that we stay awake during a 24-hour period tends to be relatively, you might shift it a little bit later, a little bit earlier, but tends to be within that same framework. Yeah, there's a few individuals that do a tremendous amount of sleeping, and then there's a few that just don't sleep. You know, and have you met any of them?
Yes.
Yeah, that was me for about 5 years, where if I got 3 hours of sleep a night, that was a good night's sleep. And I now sleep. And if you're one of these people who don't sleep, please try to figure out how to sleep. It's awesome. So all of this is really to bring us back to this issue right here, normality. And when I prepared this just a day ago or 2 days ago, I start off with normality and I flipped it, and I flipped it very intentionally. And that is, most people think all distributions fit within this structure. And they don't sort of give the chance to sort of recognize how many different ways data can be designed and appropriated. The issue with normality is not that it's a bell-shaped structure, not that it has very predictable structures in terms of variation, 1 standard deviations, 2 standard deviations, 3 standard deviations, not that the central tendencies all agree. The mean is the same as the median, is the same as the mode. Those are all kind of cool mathematical outcomes of normality. But the main issue for our purposes in normality is a lot of the early tests, ones that like Fisher created, who we talked about last time, are based on this singular assumption. And there's a lot of effort to conform data to this structure of normality in order to run statistical operations. We will talk about normality, you will evaluate normality, and you'll use those tests where appropriate. But we're also going to spend a lot of time this semester talking about alternative ways of going about testing so that you can actually deal with the data as they are. But when we look at normality, you know, it's a certain type of data structure. Can anyone think of something that is a normal distribution? Like you're like, yeah, it's a normal distribution. You'd be pretty comfortable with that.
Yeah, when you roll 2 6-sided dice, they usually group around 7 with a normal distribution.
So yeah, if you have a sort of independent probabilities and you sort of have them coexist, you'll develop a normality structure. So if you're into Vegas, that can be important. to understand that property. What about in biology? What's a good example of normality in biology?
Blood pressure measurement.
Come again?
Blood pressure measurement.
I would be surprised if they showed normality. And the reason I'd be surprised if they showed normality is because they're heavily influenced by different biological processes, everything from your behavior to other aspects of physiology to age to development, and all of those tend not to be normal. What else?
Maybe like the amount of chlorophyll in a plant's leaves.
Ooh, it tends to be incredibly non-normal.
Mm.
Yeah, because it depends on the location of the leaf, it depends on the species of the leaf, depends on seasonal effects, and you get sort of different types of distributions in chlorophyll versus an area of leaf, depending on what the leaf is supposed to be doing. I like it though.
Like the amount of drops that fall into a cup in a rainstorm, depending on like how heavy the rain is. No, I don't know, or how heavy the wind is.
That might. That tends to be random
What
within that individual storm.
It'll group and peak around one central point.
It could.
Maybe
That's not biological though.
somebody's height or like people's height.
Actually, height for a population of individuals who grow up in similar environmental conditions, human height, when you combine both females and males, tends to show a normal distribution. It actually does. Now, it has to be the same environment because human height is influenced by both genetics and environment like everything else. So if you separate out environments, then you can get different types of height structures. But yeah, within a similar population, yeah, it actually tends to show it. A lot of times we force normality mathematically through different procedures. IQ is something that shows normal distribution, but that's because of how we force that test to create a normal distribution based on the responses that people give. It's not about intelligence as much about how we manipulate the data to give you a number. So Mizia has a really good example about normal biology. My example, kind of like the dice one, is sort of a manipulation of process. And actually, the dice is better than my example. So we get normality. The big take home is there's not that much that's normal in nature. There's only a few individual cases, and yet there's a lot of things in nature we want to test and we want to study. So tests require normality. So how do we know if data are normal? And for this one, I'm going to send you guys away for really short, 2 to 3 minutes. But I want you to answer that question. How do you know whether data are normal? Any questions? Okay, see you in a bit.
All right, everyone's good with that?
Yeah, thank you.
Okay, so Riley, what do you guys come up with?
So I said you could plot your data against a normal curve and see how it fits and determine from there.
I think that is actually one of the best and easiest ways to do it. Take the distribution of the data you have, create a frequency distribution just like we've done, and then layer a normal curve on top of it. Excellent. Casey, what do you got?
So in my experience, the graphs tend to be a little bit finicky. So just plotting it over it can be a little misleading. I go about proving it mathematically. So I actually find the mean and find what percentage, like what amount of data actually falls within 1, 2, or 3 standard deviations. Because if there's too many outliers, it might look like it fits, but it doesn't really.
You know, I have never heard that answer, and it's awesome. It works. Totally fine. So we know the predictions of a normal distribution. So find the mean and then calculate what the standard deviation should be, and then look at how many data points fit within that, and is it the predicted number of data points. Very clever. Never would have thought of it. Cheers. I would never do that, by the way. No, but all you. Works for you? Great. Stephanie, the last one. What do you got?
Well, we kind of said what the others had, so I don't know. That's all.
Well, what was that? Did you say to sort of
Well, we said to
model
like
out the
observe
distribution,
mean,
or?
just observe the mean and like look at the min and max and see what range the data falls into, like, and just observe it that way if you don't do it graphically.
All right, so you kind of look at the min and max with some assumptions about what that would be. Those are fine. I will be giving you an encouragement. One of the best ways to check for normality is just look at the data. If the data look normal, and we'll talk about that later, then you can probably use those statistical procedures that are assuming normality. And if it doesn't look normal, then do something else. And ultimately, in about 3 weeks' time, we'll come up with the answer of never worry about it, and we'll just do something else. But we'll hold off on that for a few days. You can test for normality, and we're going to do that. So what I want you guys to do is I want you guys to get the dog interaction data set. And this was one of the quirkiest studies I had a student do, where they went to dog parks and they looked at whether dogs were socializing with like furred animals or differently furred animals. So did the dogs, controlling for size, did they interact with an animal that looked like them or an animal that looked different than them? So let's get that out. Go ahead and create a probability histogram, overlay a normal distribution on top of that histogram, just like we did before, which was Riley's first suggestion. And then using that sort of visual characteristic, tell me whether it's normal or not. And I'm going to send you guys out to breakout rooms to do that together. The most effective breakout rooms I've seen are people who sort of share their screen. They try things. If there's a bug, they share the screen and get some response from the rest of the group. Okay? Questions? Y'all want the same group or do you want a different group?
Same group.
You got it.
Same.
I like mob rule where the first person who speaks gets. And let me share my screen. And hey, you are in charge. Talk to me. What am I doing?
Well, at first I downloaded the wrong information, so then I had to go back and download the right one. So dogs, I think it was called dogs int something.
Do I want to start just right here at the end of this ordination script?
No.
Okay, so what am I doing?
Start a new one?
Sure. A new script?
Mm-hmm.
Okay.
I did, at least.
I think that's always a very good idea. And now talk to me.
Title it. Oh. Dogs int, I guess the same thing.
Okay. Does it matter?
Yes.
A little bit. It's always a good idea to use a title and a variable that you understand, but you can do anything that you want. So keep talking. What am I doing now? What's the first code that we tend to type in? It's either going to be library or it's going to be what? And we are a collective class, so you are always welcome to interject.
You could run library hmiss just to make sure it's on your R.
Yep, I always think it's a good idea to put into packages, and that will become increasingly important throughout the semester. So now, Tara, what do I do to get dog interaction into R?
Go to import dataset.
Oh, you want to do it that way? Sure.
Oh, I did it. I'm probably not doing anything right, but yeah, that's what I did.
No, you can do it this way. It's a little more advanced, and it can get a little squirrely in some type of data. So I'll show you guys this, but normally I would encourage you to do the read.csv for right now. Later in the semester, I'll show you about how to do this, but we're doing it, so let's do it. So we're gonna browse. Let's go find our folder. And this is where we have dog things. We hit that. That gives us a name down here. We have our two sets of variables, intx, social. We can define what they are. Double means that they could be treated as characters or numbers, so we'll keep it at that. This is the code that's going to be put in to do this. And you can say, go. And now we have the data in there. That will, and I like copying out the code into our script, so we can just have it next time. So yeah, that works. That was pretty advanced, by the way. And
I
again,
actually did that, so I don't know how I.
hey, if you got it, you got it. Do it. And as with everything in this class, if it works for you, do it. I'm going to teach you the read.csv now because one, you understand why you're doing certain things. And two, it doesn't tend to be as buggy. There's a little bit of bugginess with the import data set if your data sets become a little complicated. But yeah, that was cheers. Wow. Astrid. Regardless of what we did before, what do we do now? There are 3 lines of codes we always type in. I see Astrid. Not yet. So let's come back. Ryan, I know Ryan's not here. Kayla.
Are you talking about the read.csv part or like the attach and names?
Yeah, we cheated. We did a different version of read.csv. It was kind of cool. It was pretty advanced. It was awesome.
I'm
So
just
let's
making
go.
sure we didn't need to do that. So we use attach and then the file name.
I'm assuming dog index is our file name. Next one.
Names.
Next one.
And then describe or summary.
Yeah, go and just start using describe. We use summary for a few other things, but summary no longer reads categorical data the way we expect. Awesome. So we run those, we get our attach, we get our names. Oh, because I didn't do this first step. Now we run our describe and we get our describe. We have 2 variables. It's always kind of a good idea to take a look at them. We expect this to be continuous. Dog, the interaction variable, because it's an interval. It could be 0, but then the infinite number can be anything. So that's an interval. And then social, this is a percentage of time, 0 to 100%. So it's ratio data. And it's a good idea to make sure that you have means in both cases. So that looks good. Awesome. So Mike.
Yep.
Talk to me.
All right. So then next I did hist, H-I-S-T. And then in parentheses, INTX, comma, then enter, prob equals T. Enter a capital T. And then enter after you put a comma. And then breaks equals, I probably should have changed this because the data set, but I left it at 25 because that's what we had last time.
That just defines the maximum number of breaks that would be put into the histogram. You always want to have it less than the data set. And it's a good idea to like it, at least be like a third less than a data set, but R will make assumptions based on how you're doing it. So can I hit run?
Yeah.
Oh.
Oh yeah, you have to.
So Cortland.
To fix the error, you just drag the right side of the screen towards the middle so that the plot window has space to show the plot.
Oh, right, because our plot pane is too small. So we open that up. Didn't fix it.
You have to run it again.
Oh, thank you. Oh, wait, that looks good. Looks good. We'll go with that. So then, easy.
So then I put curve. I did INTX, well, parentheses INTX. Oh wait, no, sorry. I was looking at the wrong part. It was denorm. So get rid of the INTX.
Gotcha. Keep going. You're doing perfectly. So we did D norm. Oh, I think you froze, Measy, so we'll move on. I'll get you when you come back in. Dominique, Lynch.
All right, so then after the second parenthesis, you're going to put X, comma, space, or enter, under. You go under. Hit enter.
Ah! What happened?
Sorry, I just like froze up when I was speaking before.
Oh, not a problem. You're good. I will come back to you in just a second.
Okay.
So Dominique, go ahead.
And then you're going to put mean, and then equals, and then you're going to find it from the describe.
How do we cheat? How do we cheat? How do we cheat? How do we so we don't have to find it?
You can just put int or intx, right?
Let's not look it up. Let's use code to do it for us. And we got an idea? We're gonna try to cheat a bit. Make our lives a little bit easier. We need the mean of intx. So how do we get it?
Look at the summary.
We could. We
You
could.
could just put mean in parentheses INTX.
Ooh, love it. I'll get you the same thing. So Dominique, keep going, but now I want you to cheat.
Do you need mean twice right there or no?
I do.
You do?
What is this one doing?
That
What
one's
is
saying
the
that's
highlighted
the
doing?
mean. Okay.
And what is this mean doing?
That one's saying to get the mean of that.
Bingo. So now I want you to tell me the next line using the same logic.
All right, so you're gonna do SD
Okay?
equals SD, and then in parentheses you're gonna put INTX.
Awesome. Awesome, awesome, awesome.
And then you're gonna put a comma.
Here?
Yeah.
Here. Go
And then
ahead.
you're gonna put add equals and then T. Capital T.
Thank you. All right, let's do it. You guys ready? Oh, why didn't it work? I hit enter.
You hit
Nothing
enter.
happened.
You have to hit run.
You have to hit run. Oh. You have to hit run in the right part. Did that work? Are we happy with that? Okay, I am exceptionally lazy with code. So I would like, Joe, you here? I don't think I saw you. Ipti, I am very lazy with code. I do not want to rewrite all the code.
You
But I
can,
want my answer. How do I get my answer?
sure, you can just select, when you go to his, like just before the H, and select all the way down to T. Yeah, and then copy paste it, like
Copy,
below it.
paste.
And all you need to do is change the INTX to social.
So here's a little trick. You can go up to find and replace. Maybe. Try again. That's not going to work right now. All right, so I'll get that later. So what do I type?
Social. Yeah.
Anywhere else?
And in the mean, like instead of INTX, like put social. And same for the standard deviation.
Okay, let's do it. Okay, those are pretty good. Now, I want us to look at normality for both of these distributions. right now, can we see both distributions? No, so I would like someone to help me figure out some code we can do so that we can actually see both distributions, so one is on top of the other. And that person, Alana, can you give me some code or some ideas of what we might want to do?
I was still messing with my code when you asked the question, so can you repeat?
Yeah, we need to put a line of code here in 10, row 10. That's going to allow us to create a single plot with two figures, one figure on top of the other. Got any ideas of how we could do that? So right now our two plots are on
The
two
only
separate.
thing I can think of is parameter. Or
Ah, good. Par. Remember what we do now?
No, I don't remember.
That's fair. This is more advanced. So does anyone have an idea of what we could do? We're going to change our parameters. Riley, go ahead.
Well, what I did is what was in the homework. I just typed mfrow equals C, and then in parentheses 1, 2.
1, 2 will change the column. I want to change the rows.
Oh, then 2, 1.
Comma 1. Let's try it. So we run it. Okay, nothing happened. That's fine. We get, oh, that's looking pretty good. We got our histogram on top. We get our curve on top of that. We get our histogram at the bottom. We have our curve on top of that. So now we have both sets of figures on top of each other. Can we use this to look at normality? Do these data look normal? I got one person saying no, and I've got roughly 25 people on my screen just looking straight ahead. So are these, do these data look, now I got 2 that say no. I haven't really figured out the poll quiz function in Zoom. I'll try to figure that out. But by show of hands, how many people say, yeah, this is normal? Yeah, these look good. All right? By show of hands, how many people say, no, these are not normal? And I like Tara. Tara's like, yeah, I'm going Switzerland on this one. I'm not going to really say one way or the other, which is fine. We're looking at the distribution to try to get a sense. We put the curve on to help us see that distribution, but you know, we have some weird data points. And it's not like it's just skewed. It might be a little skewed, but then we have some values that are a lot more than expected, and other values which are a lot less than expected. Now, we would get a slightly different visual if we change the number of maximum breaks. Let's try that. So we run that. Oh, looks a little different. Run this. Looks a little different. Do they look a little more normal now? We could try 8. Now we get that curve. Now we get this one. It's starting to look a little bit normal. Should we be changing the visual representation of curve to demonstrate normality?
No.
No. Let's cheat when it's valid, good science, but let's not cheat when it's sort of making up stuff. And you can change visual representations, and that will change how things look. All of those figures that we made, they're all accurate, they're all honest, but based on how they're represented, you can sort of change how a person might respond to it. So there are alternatives. Visual is a good thing to do, but we can run something called a Shapiro-Wilks test. And this is a test that people use a lot before doing any thorough analyses. And this test evaluates normality. So you run this test, and depending on the p-value, you have evidence for the data either being normal or not normal. There's something really weird, though, about the hypotheses associated with this test. Anyone see within the notes? What's a weird hypothesis associated with this test? Daniel, is that a stretch or you want to answer?
That's a stretch.
Ah, I was so excited. So excited. So Madeline, you're up. Looking at the notes, what's really kind of weird about the hypotheses and what this test is evaluating?
Well, I think it's a little strange that if the data are not consistent with normal distribution, they are normal.
Yeah.
Okay.
So the null hypothesis in the Shapiro-Wilks test is normality. So the null hypothesis in the Shapiro-Wilks test is normality. The alternative hypothesis is non-normal, which means if you have a large p-value in a Shapiro-Wilks test, then you have data that are consistent with normality. If you have a small p-value in the Shapiro-Wilks test, then the data are not normal. That makes sense? And so it's backwards the way we normally think about a null distribution. In this case, the random distribution is normal. And that's why the null hypothesis is a normal distribution. So let's play a little game. Mitch, I saw you, right? Yeah, I see your name. Mitch, Mitch, I'll come back to you. This is one of the reasons. Keep the mute on. Forrest, p-value, 0.4. Are those data normal or not?
They are not normal.
They are normal. Try again. Let's
Oh,
go.
0.4. I was thinking 0.04.
Yeah,
Sorry.
yeah, that's totally
Sorry.
fair. Daniel, p-value, 0.5. Normal or not?
Not normal.
Normal. Very nicely done. Ben, p-value, 0.03. Normal or not?
0.03 would be normal.
Not normal. Small p-value, not normal. Rotella, p-value, 0.9. Large p-value. Are those data normal or not?
Normal.
You're muted. Normal. Very nicely done. Love it. Okay, so Isaac. Did I see Isaac? I did not see Isaac today. If Isaac is okay. Dakota Crawford. Do not see Dakota Crawford today. Tristan, you're up. P-value, 0.1. Normal or not?
That would be normal.
That would be normal. Very well done. Courtney. I saw Courtney, right? Courtney, p-value, 0.002. Normal or not? I see Courtney? I thought I saw Courtney. Oh, we'll come back. We'll come back. Dakota Rivers, same one. P-value, 0.002. Normal or not?
Not normal.
Not normal. Perfect. And then last but not least, Elianis. P-value of less than 0.001. Normal or not?
Not normal.
Not normal. So the system runs opposite the way we normally think about it. Random in the Shapiro-Wilks test is a normal distribution. If it's a large p-value, 0.4, those data are consistent with normality. If it's a small p-value, 0.004, those data are considered not normal. Make sense? Running that code in R is very simple. It's Shapiro.test, and then the variable x is whatever variable you have in your data. So intx and social. Please check.
So what we just run it against X?
You need to change X. X is just a variable. So change it to the variable names in R. Okay, one more minute. All right. So Morgan, you're up.
Yes.
Tell me what to do. You talk, I type. You're in charge.
Okay, I was finishing my code, but so far what I did was the Shapiro period test, and then instead of X in the parentheses, I did social,
Okay.
and I ran it.
Oh, that looks like it worked. So, Logan, please interpret the statistical pattern. Are these data social? Are they normal or not?
Not normal. Or no, they are normal.
They are normal. They are normal. Even though this figure looked like this, Shapiro Wilk says that they're normal. Riley.
So what would you consider the like threshold for the p-value for this between small and large?
0.05.
Okay.
Is the universal threshold that applies in most situations. We will talk about cases where you may want to do a different p-value, but we'll do that a little bit later with different data sets. But all things being equal, if no one talks about it, the threshold is 0.05. And can someone remind me what the logic is? And there's 2 points of logic that you can use to argue why we say it's 0.05.
If you're only wrong 5% of the time, you don't care that much?
Yep. It accepts a 5% chance of error. And that's, that's actually pretty reasonable. Now, if you're doing cancer research, or let's be a little bit more timely, if you're doing COVID research, do you want to accept a 5% chance of error? Or is that too high?
I think the errors rate on the death reports are like 200%.
Yeah. But the point is that might be too high. So in that case, you would want to have a lower threshold. And to have a lower threshold, you would reduce your p-value to maybe like 0.01. And a lot of times, if we're studying small sample sizes, like endangered species, we might increase our p-value to 0.1 because there's just not much data to evaluate. And we still want to understand whether there are patterns. We just accept a higher % chance of error.
Yeah.
Well, things being equal is 0.05. Okay, so good. So now, Heather, B, you're back up. We did social. What do I want to do now?
Excuse me, Shapiro dot test, and then INTX in parentheses.
Okay, what do I do?
Run it.
All right, and Alex, are these data INTX, are they normal or not?
For social, social is normal, and then for INTX, it is not normal.
Perfect. So we're going to use a combination of looking at figures, but you can also use these tests to decide whether you have a normal data or not. That is needed decide what type of test that you are going to do later. We do not report this value unless you're doing it as a homework assignment or as part of an exam. But if you're doing science, you'll test for normality, but you're not going to report it. What we use it for is part of our methodology in order to decide how to analyze the data. And we look. So there's an issue. In the case of the interaction data set, these data are not normal. You know, it's a pretty small p-value, 0.01. What do you do if the data are not normal? And without being pedantic and facetious, exactly what I said in this slide. No big deal. There are so many ways of addressing non-normal data. And importantly, since we're biologists, we want to address the real data and the real distribution. So if your data end up not being normal, there'll be a lot of ways of getting around that. When you have non-normal data, some of the things that you should do is just look at the data. If the data look normal-ish, then don't worry about it. It's close enough that it's not going to really affect the overall results of your stats. If they're a different type of distribution, you may want to consider transforming, but there are also ways of adjusting to that statistically. And you may want to just use those adjustments. And then sometimes our data are just fundamentally bizarre. And in those cases, you don't want to force normality. What you want to deal with is you want to deal with the distribution as is in order to do analysis. And we'll be doing a lot of things like bootstrapping our data and using non-parametric approaches. So if the data are not normal, there are ways to get around it. If they look normal, don't worry about it. If they kind of have a skewed data, then we can transform it. Or if they are weird, which is most of biology, we have other approaches to deal with it. Another way to visualize data are something called QQ plots. And these are sort of the standard visualization approach. A histogram with a curve on top will work. But QQ plots, these quartile plots, are the way that most mathematicians and statisticians will visualize normality. Because what you are looking at is you're looking at the distribution of your data relative to a theoretical distribution of normality. So that if your data points align along this distribution, along this solid line, then your data are basically normal. Some of the nice things about QQ plots is the way that the data is structured. Maybe like you have a curve that goes on the realized side or a curve that goes below the realized side can help you visualize what the actual distribution of the data are. If there's a straight line, then you have normal. If it is going above, then you have left skew. If it's going below, you have right skew. If it is uniform, unfortunately, uniform looks like normal. A kurtosis gives a sigmoidal shape. Bimodal gives a stronger stepwise function. Each of these, if you get comfortable and practice with it, becomes something that you will see in those data. I'm not going to require that you understand how to visualize all the pieces, except being able to look at how the data points line up, says normality, or if the data points do not line up with the center line, that suggests non-normal. What I want you guys to do is I want you guys to create some QQ plots with the data from the dog interaction. So we can look at how those data line up relative to the idealized normal distribution. Let me copy both of these into the chat. Then I'm going to send you out into the breakout rooms for a few minutes. Hey, go and grab those instructions before you head out. Mitch, Madeline, let's head out to the groups. Any thoughts?
What do you mean by thoughts? Like, just how it went?
Yeah, and whether it's reasonable to include normality in the exam.
I think it should be reasonable. I mean, they have plenty of time to study it. I know that it's a lot of like things memorizing, but what do you think? Do you think that it should be?
I would kind of like to, so that we can kind of conceptually move into the next step. I don't think we can do outliers and transformations, even though I will talk about it for a bit.
Okay. The QQ plot, I wouldn't ask questions on that, right? Like
I think the only thing I might do with the QQ plot is I may actually show
from the left side, right?
What's that?
From like the left side of the PowerPoint, not.
Yeah. I will do nothing more than, and I'll show this one. I'll do nothing more than maybe show a QQ plot and have data that clearly depart from that line, and ask whether they're normal or not. Or find data that line up with that line very precisely. Are they normal or not?
Okay.
And I think nothing more complicated than that.
But yeah, I'm excited to see what they for the next discussion after that, for what they do if their data is not normal.
Yeah.
For them to fall into that trap.
Yeah.
Yeah, I did I was looking at my code from last class, or from not last class, but last time I took this course, and I didn't put titles, so you can't really tell when you do the QQ plots which is which. And so I just fixed that.
Yeah. It's the farther you go along in your career, the more anal you become about naming things, because there's just so much.
Oh yeah.
And trying to make use of it becomes impossible.
I started my what was it? My theme, like.
Can you see our screen?
Yes.
Yep.
Thank you. We still got a few people coming back. So let them get back in.
So QQ graphs help you analyze the regression, or like the central or tendency towards normal distribution?
Yeah, QQ graphs are the standard way in which a person visualizes normality. If the data points, which are represented by the circles, basically sit on this theoretical line that describes the standard deviations of the normal distribution relative to the measured distribution, then that is considered normal. If the data points do not line up on that one-to-one line, then it's considered not normal.
Okay, so if there's.
Tristan, you broke up there, buddy.
Yeah, it's okay. Sorry, but I get what you're saying. Thank you.
Yeah, okay. So let's do it. So I need, well, Riley, you're up, buddy. Tell me what to do.
Okay, so you start with typing QQ norm, then in parentheses, INTX.
Okay.
And then QQ line, in parentheses, INTX.
Okay, let's do this first one. Okay, great. Casey, why is my plot only in the top half and not in the entire plot pane.
Maybe just because you have the plot window. I wonder if you were to move it over like that, if it would make it. Ooh. Would it make it taller? Try moving it smaller. No?
Heather, does your hand?
Yeah, because the parameters are still changed from when we changed it earlier.
Yep, that parameter function is still active. If you wanted to change the parameters, you would just add a line of code to do it. But in this case, I don't want to change parameters. I want to keep them. Well, actually, no. Let's actually do it. Let's cheat. Copy. Paste. And we can just do 1, 1.
So in order to reset the parameters, you would just have to clear the code in the console?
Yeah.
Okay.
Okay. So that's INTX. And now, Stephanie. Next one.
Oh, okay. For the next one, I did basically the exact same thing, just social.
Okay. So talk to me. Tell me what to do. Are you talking?
Yeah, sorry, I said something and you didn't respond, so.
So tell me what to do.
Okay, QQ norm. Social, parentheses, social.
Awesome. Okay, I'm going to read your lips. When we run that, when we get that. Okay. These are devices. In this first one, this is considered relatively normal. The vast majority, especially the first two standard deviations, they fit the line pretty well. There's a little bit departure towards the edge. And the next one, we see a little bit more departure both on the high and low side, which really reflected that these data had a huge skewed structure to it. So if these individual data points match the line, you can pretty much make a strong argument that the data are normal. If you have things, especially at the tails or in the middle, that are not hitting that line very well, then you have a case for non-normal distribution. So a lot of data have some pretty weird things. I know we have 10 minutes left. The exam material will stop in normality, but I still want to do this piece. So please grab the Heron data and take a look at a QQ plot of strike per minute. And no, go and stop. That's just me forcing an issue. We're going to stop there. We got 10 minutes left. There's no reason to try to rush through one little more piece and then have to come back in next Thursday. We have the exam on Tuesday. Any last questions, especially about today's material, which will be on the exam?
So Professor, you said for the last thing we did was par MF row equals C. You said when you do that, it makes it more, it makes it look better or something.
It allows you to change the number of graphs you see in the plot plane. Right now, we only have one row and one column. So that means that we're only going to see one figure in here.
Okay.
If I make that, well, actually, let's go 1, 2 in this case. I set this up. What we'll have is one row, but two columns. So if we run that, we'll get two figures that basically line up next to each other.
Okay. Okay. Understood.
Anything else, ladies and gentlemen? All right. Have a lovely weekend. Do something fun. I'll see you on Tuesday. Go to class together. Take the first part of the exam.
Thank you. Have a good weekend.
Thank you. Have a good weekend.
Thank you.
Thank you.
Thank you.